Hi, and welcome to Lecture 11 in my series on Introduction to Quantum Theory and Technologies. Up to this point, we've been talking mainly about just single quantum systems. So, if you just have like one quantum system, how do you measure it? What are its properties? How do you make observables from it? Um, but things actually get really interesting when you start to put more than one quantum system together. This is what we're going to talk about in this lecture, and this will lead us on into talking about topics like entanglement, which I think some of you might be already, you might have heard of it somewhere or even be familiar with it, but it's one of these main components of quantum mechanics, which makes it something very different and distinct to classical physics. So that's what we're going to talk about today. Just jumping right into it. Uh, how do we define more than one quantum system? As I was saying, up to this point, we've just been talking about sort of single quantum system where the wave function is given by something like this. We've got, like, say, d levels, and in general, a quantum state is written as some kind of linear superposition of these d levels, where these coefficients here are complex numbers and they need to be normalized. Um, but what if we have more than one of these types of systems? These characters, Alice and Bob, this is not something that I've made up. This is actually sort of now the common way of talking about more than sort of one system or one party. And it's very convenient kind of notation. So as soon as you say Alice and Bob to anybody that's working in the quantum information world, they know exactly what you're talking about. We're going to use the same kind of convention where Alice has one quantum system and Bob has another quantum system, and we're going to look at the quantum states that can be made between these guys. Okay, uh, basically the idea is quite similar to what we had before. So if we recall, how do we make a quantum state? What we did, how I explained it to you before, was that these states, which I label by n, are some distinct quantum states of a quantum system, right? So, for example, these levels here, uh, I've drawn this sort of like a bit like an atom. So these could be like energy levels of an atom, but they could be pretty much anything where the states are kind of distinct. So these could be also like positions of some particle with distinct, places. Say, a particle is in a box and it's in one of the boxes. Or it could be any other quantity, like momentum, like the speed of a particle, or anything like that. So um, we enumerate our quantum levels according to some distinct quantity of the system. So here we've got two systems, and just for the sake of example, I've got two three-level systems. And so the distinct states of the whole system can be described by basically all the different combinations of states that you can have uh, between the two systems. So, for example, if we've got two systems here, the first one here is the one held by Alice, and the second one here is held by Bob. Then, for example, if both Alice and Bob's systems are in this state 0, that's one distinct state of the whole system, right? Likewise, if Bob's state was 1 and Alice was 0, well, that is different in a global sense. This pair of states is certainly different to this one because Bob's state is different. So we can immediately say that, yeah, that's a different state. For example, if we've got 3 levels, then Bob's state could also be in level 2, and that would be a different state. Of course, Alice's state could be different. It could be saying state 1 and 0, 1 1, 1 2, 2 0, 2 1, 2 2. Right. So in this case, there are going to be 3 times 3 because there's 3 states on each each quantum system, and there's 2 of them. So there's Alice and Bob. So there's a total of 9 different combinations. So 9 different distinct states that this composite system can be in. So the way that we write this mathematically is using the so-called tensor product. So I won't really go into detail of the mathematics of the tensor product, but basically all you really need to know is that this tensor product is a way of making like uh, a larger vector from 2 smaller vectors, right? So, for example, if this first one is the state of Alice, and so this vector is like, say, 3-dimensional, and say Bob's vector also is sort of 3-dimensional, so there's like 3 different values of NA that this could take, 3 different values of NB, then this whole thing is like a larger vector that is in this sort of 9-dimensional space because basically all the different combinations of NA and NB, there's 9 different combinations. So tensor product is a way of forming like kind of a larger vector from two smaller ones, right? So that's kind of the mathematical way of writing the composite system. So here, this NA and B could be any one of these 9 states here, right? According to the different combinations of NA and NB. Now, often physicists, and me included, and in fact, I'll immediately switch to this notation. I'll just drop this O times because basically anytime you see these 2 vectors just next to each other, it's sort of just implicit, right? So I often just kind of drop this O times, even though that's like the proper mathematical notation. If I see 2 vectors just lined up like this, I'll take it to mean this kind of composite system that we're trying to make. And I'll even sometimes write it in this way, where we have NA and B inside the same state. And the reason why I can do that is basically because each one of these combinations is a particular quantum state, right? So that combination is a quantum state, and so because that is a quantum state, I might as well just label that whole thing together as a quantum state, and so that's why I just put it inside the single ket here, and then we need like 2 labels here just to know which state that we're talking about. So 0 0 0 1 1 0, or so forth. So further note here is that if I'm using this this notation here, or even this one here, I should always keep the ordering of these things in the same ordering. So I shouldn't like swap the orderings just out of nowhere. So basically that means that the first state here is always Alice's state, and the second state here is Bob's state, and that ordering is always fixed. Don't go changing that label, because obviously then you'll get a totally different state. So it's kind of implicit that the first one belongs to Alice, and the second one belongs to Bob, even if I don't have the A and B labels here. Okay, and that the same goes for that notation too. And in fact, here too, I mean, obviously, if you start swapping the labels, if I wrote like 1 0 here, and then I just in the middle just suddenly decided to change it to 0, 1, then all of a sudden I'm talking about a different state. So obviously I shouldn't be doing that. So don't change the orderings of these labels ever. Okay, so that's how we denote the distinct classical states of the system. Now, how do we make a quantum state? Well, as you can imagine, we can make a quantum state. Now, if we're saying that any one of those combinations is a distinct state, then we can make a full quantum state using those by just taking any linear combination, as in we just multiply it by some complex number, and then we add over all the different combinations, right? So in this case, in that case with the 3-level atoms, essentially each one of these combinations has some weighting, which is denoted by this thing A, with two indices here, and each of those indices are of course complex, and then we add basically all these terms together. Right? As usual, if we want this whole thing to be a quantum state, then we need these coefficients to be normalized. Right? So that ensures that the state, when you take the overlap with itself, sorry, the font of this one should be the same as this one. So when you take the overlap of capital psi with psi, that should be equal to 1. And to do that, what we need is these coefficients a mod squared summed to be equal to 1. So just like normal, except that now we've just got kind of like more combinations of different states. Okay. Again, often I won't write it like this. I'll just abbreviate this O times, the tensor product symbol. I'll just drop that, just make it implicit, or even write it like this. So same thing as what I said last time. Okay, so let's just look at a particular example here. So actually the most common example that we'll be talking about is 2 qubits. So as we had before, basically the 2 qubits, we want to look at all the different combinations of states. So 0, 0, 0, 1, 1, 0, 1, 1. First qubit is held by Alice, second by Bob, as usual. So there's a total of 4 different combinations of states for the composite system, and each of them have some coefficient. Okay, so we have A0, A01, A10, A11. Okay, and these things are always normalized. Okay, so that's the kind of thing that we'll be often dealing with. And we'll come back to this example in a bit later in this lecture, but first let me tell you a little bit more about particular special classes of quantum states. So uh, you might say, so okay, we can make a composite system by putting together two systems. Okay, so I've told you basically the rules of how to do that. So one question which you might have is, so can we just put any 2 quantum systems together? So the most common case that you want to sort of consider 2 systems as a whole is because maybe, they're part of the same, they're just right next to each other or something, or, you want to look at a particular device and it's got 2 particles in it, so it's natural to think about it. Now, in that case, it's maybe natural to think about that as a composite system. But what if I just took any 2 particles? Say one particle was here and on this side of the Earth, and the other one was on the other side of the Earth. Can I take a composite system with those two particles? And the answer to that is actually yes. So there's nothing to stop you from just basically choosing any two particles that exist in the universe and then making a composite system. So it's really it's a matter of your choice of what you want to include in your system and what you don't want to include in your system. So, for example, if these particles were just totally independent, what would happen is that you would have actually this state here where, for example, let's say that Alice's state here is in the state psi A and Bob's state was in this state psi B. Then the total composite system you would write like this. So you would just say it's like the tensor product of psi A and psi B, where psi A could be actually any state, even with some particular, coefficients here, like A with some coefficients, and Bob's state also could have some coefficients, B like this. So in this case, the state, we can actually sort of write this out. So for this particular example, remember this is sort of a special case here, the state would be written out like this. So we'd just basically substitute that in here. And the way the tensor product works, it's basically just like kind of multiplication. So whenever you have this multiplication, you can basically run the sum over the two indexes out the front here, and then we have the wave function written in this form. Alternatively, for the case of qubits, or just to give a more specific example, it would be something like this. So A0 times 0, A1 times 1, tensor product with B0 times 0, B1 times 1. Okay. So so this is basically how you'd write independent states. And it turns out that there's actually, the reason why it's kind of up to your choice of what you want to include in the system is because for these types of independent states, it doesn't actually matter whether you basically include it there or not. You can always get the same result, whether you sort of include it there or not. And now, so I'll show you now how exactly that works and why you have this kind of freedom of choice of basically including an independent state in your composite system or not. Okay, so to basically show this, I want to first talk to you about how actually measurements work on composite systems, right? So basically what I want to do here is say now I've got like say two particles. So the two particles form some composite system, and now I'm going to do some measurement on it. So, so how do measurements work with composite systems? So the answer is it basically works in exactly the same way as as we already know. So all we really need to do is just sort of extend the measurement idea to sort of a larger system. So for example, for 2 qubits, there are kind of 4 states in total, as we saw. So when you do a measurement on 2 particles, you will always get sort of 4 outcomes, right? 4 different outcomes. And these 4 states, you can basically, again, as we were talking about with the idea of, you can do any a measurement in any different basis. So these 4 states could be in any kind of basis that you choose, right? So that means that basically what happens in this two-particle case is pretty much just like what we saw before. So provided you've written your wave function in terms of these four measurement states here, so S0, S1, S2, S3, S I guess stands for state, so state 0, state 1, state 2, and state 3. So provided you've written your wave function like this, then the probabilities of getting it from this measurement machine here is just the usual mod squared of the these coefficients. Okay, so basically nothing really conceptually new there. But what's actually a little bit more common is that each particle is measured separately using a separate device. And, I mean, this is sort of basically like a real world issue here because generally, it's a little bit more difficult to measure the kind of the composite system because, particles have their physical identity. So that means that, one particle is here, that's one quantum state. So it's natural to basically measure that particle. And if you have your second particle, it's natural to then measure the second particle sort of separately, right? Um, so, uh, so what's a much more common situation actually is that so Alice and Bob each have their particles. Each of those particles go into the measurement machine, and again, like we had in originally, say if these were qubits, then there would only be two measurement outcomes for each machine, right? Because you're still measuring this single particle here. This is a single particle measuring machine, so there's going to be like two outcomes for each machine, right? So there's two outcomes for two machines, but there's still all the different combinations that could happen, right? So so what could happen is that Alice could get outcome say 0 and Bob could get 0, or Alice could get 0 and Bob could get 1, or Alice could get 1 and Bob could get 0, or Alice could get 1 and Bob could get 1. So actually there's still the four combinations that we had. And so we still, if we take kind of this, uh, these two boxes together, we can regard that as our sort of two-particle measuring machine, right? So it's just that, each machine, we've just kind of got two machines, but, just block the whole thing, then we still got like our four outcomes. So this is the more common way that you'd actually be measuring the particles, right? So in this case, in terms of what I was saying before, we have still these four measurement outcomes, just S0, S0, S01, 1011. And provided we've written our wave function in terms of these four outcomes, then the probabilities that we get there are still like squares of these four cases, right? Okay. So let's go back and talk about that independent state example again. So what if we have this independent state where we've got this, product form of the wave function. So these are basically particles that, don't really know that each other exists. They've never met. Maybe they're on opposite sides of the world, right? Okay, then, so we've got this state here. Now, um, it looks like we might get kind of a different answer because we've got this B here. So for example, suppose Alice, this first one is Alice, goes and measures this second particle. And, she has no idea that Bob on the other side of the world is also doing some kind of measurement of his particle. And and what I was saying before is that, we are kind of free to include Bob's particle or not, right? So we have got kind of that freedom of choice. So we really should get consistent results in either case of if we included this Bob's particle or not. So what I want to show you here is that you do indeed get basically the same results as what we had before. So for example, if Alice gets the outcome 0, then that case could, in terms of this two-particle measurement, it could be that Bob also gets 0 or Bob gets 1, right? So really the outcome of Alice getting just outcome 0 in terms of this two-particle measurement is really the combination of two cases of when Alice gets 0 and Bob gets 0, and Alice gets 0 and Bob gets 1, right? So what we were saying as, if we sort of just kind of cover up this, say this second box here, what we had before was just, particle 0 being measured. But in the context of this two-particle measurement, that would actually be two cases. So the probability of only getting 0 is really just in this two-particle case, it's like this P00 and P01, which are the probabilities of those two cases, right? So in the case of this independent wave function, if we just go and calculate these probabilities, so P00 is this A0, B0 mod squared, and P01 is A0, B1 mod squared. And the total probability, as in the probability of Alice getting 0 and not caring about what Bob got, is going to be basically the sum of these probabilities. And here, because if we add these two, then the B0 and the B1, this is normalized because this is a normalized state. So this just becomes 1, and we get P0 is equal to mod squared of A0, just like we had before. So it's the same result as if psi b was not there. So this basically shows that you can actually just tack on this additional independent state, and as long as basically you add over all the different cases where you get the result that you are talking about. So in this case, this result 0. If you add all the different cases, then basically you still recover the same probabilities as you did before, even with the this composite system approach. Right? Okay, so was this, it kind of looks kind of like lucky almost, that I just sort of added these probabilities and then it became independent of this B, and I just get the same answer as before. Was this just luck? So no, it's not just luck. It's actually just this is kind of how these probabilities and how the states are constructed. So the way that basically another way to sort of show this is to for example, if we use the measurement operator approach, then we can actually write our measurement operator also in terms of this kind of tensor product. So in the case of Alice doing a measurement, then the first one is Alice. So we've got our measurement operator here, and in the case of only Alice doing this measurement, then we would put the identity matrix here. And so if you use that as the measurement operator on the composite system, then what happens is that this M just acts on Alice's part, the identity acts on Bob's part, and basically Bob's state is left untouched where this measurement operator acts on Alice. then we can go and calculate probabilities. Then if we do the same procedures we sort of used to, we take this state, take the overlap with itself, then we basically always recover the same expression as we had before, where it's just the state on Alice that's involved, and the state here on Bob is, just basically disappears because so this part here is just equal to 1 because basically Bob's state is normalized. Right? The new state here, then you just divide this by the square root of this probability, as we've done before. And because this thing is just a number, we can just collect it on this side here. And basically, it's just Alice's side that has these terms here, and Bob's side just remains completely untouched. Right? So the second state just sort of goes, so Bob's state just goes along for the ride, for this case of the independent states. So this is basically why you can just tack on some, independent states, and it never really affects any final results. Right? So, yeah, okay. So this is how sort of measurements and independent states kind of work. So what if the state isn't independent? So the way that we wrote these states, so this was the case of the independent states. And what you should notice here is that actually this type of the coefficients here, this is actually a more specialized kind of form than the more general case, right? So that means that you can write, it's possible to take this more general form as an independent state, but you cannot choose these coefficients here um, in a way such as to make any possible state here. So basically, in terms of like kind of a Venn diagram, this general state is has a wider variety of states that that this can sort of denote than the independent states, which are more kind of specialized, right? So these are kind of there are kind of two basic classes of states. Ones where you can write in this kind of independent form, or states which you cannot write in this form, and this is what actually is the more formal kind of definition of entanglement in terms of the pure states that we're going to be looking at here. So for mixed states, they have a slightly different definition, but we're not really going to deal with mixed states, just pure states here, which can be written in this form. So entangled states are really nothing but states that you cannot write in this independent product form. Okay, so let's just look at an example because I think that will give you a better feel for it. So let's consider the most general 2-qubit state. So this can be written as some linear combination of these states. Sorry, I've messed up the notation here. So this should be 1, this should be 1, and this should be 1 and 1 here. Okay. So that's the most general state that can be written. For the independent states, this can be written in this product form here. So if we multiply this out, so we get coefficients like this. So there are some states, as I was saying, that you can write in this first form, but you cannot write in the second form. And I'll give you one example here. It is this particular state where we've got coefficients only on the 0, 0, and 1, 1 states. So in other words, this state here, A01 and A10, are both 0. And in order to normalize it properly, I've got this 1 over root 2, which normalizes. Okay, so why can't we write this in this form? So, well, we can actually easily sort of show that. So what we need here are this term and this term to have be 0, right? Okay, so if we need this and this to be 0, so as in A0, B1 and A1, B0 to be 0, then, for example, let's try taking A0 to be 0, right? Okay, so that would satisfy this equation. We really need one of these things, or maybe both, to be 0, otherwise this thing's not going to be 0. Right? So let's take A0 to be 0 just to start. So if A0 is 0, then that automatically makes this other term, A0, B0, also equal to 0. So I cannot choose any value of B0 to make this equal to the 1 over root 2, which I want it to be here. So that means that I can't set A0 to 0. Likewise, I can't set B1 to 0 because that would also make this term equal to 0. And then from this equation, I can't set A1 to 0 because that will make this to 0, and I can't set B0 to 0 because that will make this term 0. So there's basically no way of choosing these coefficients such as to write it in this form. So this basically just goes back to my point that the example of the state that I had there is a type of entangled state, and basically it's impossible to write it in terms of this form of independent states, right? So this state kind of lies somewhere out here. Okay, so this is actually where things get pretty interesting. So this type of state, entangled state, has some types of quantum, has some correlations. And what I want to talk to you about in this part here is how these states actually have some so-called quantum correlations, where it actually has some very mysterious properties, and apparently there is some effect that you can make between Alice and Bob, despite the fact that they might even be separated by very large distances. Here I've drawn it on the opposite ends of the Earth, but maybe they can even be at opposite ends of the universe. It seems to be not limited to anything related to distance, right? Okay, so first, uh, first let me explain how these things are correlated, right? Okay, so we can see that these things are correlated because, for example, if we do a measurement, and say we do it in 2 steps this time. So say first Alice makes a measurement. So if Alice makes a measurement, then what happens is that because we know that the only outcomes that when Alice and Bob make their measurements, the only outcomes that we're going to have for this case are the outcomes of when Alice gets 0 and Bob gets 0, and if Alice gets 1 and Bob gets 1. And each of those happen with the probability of half because if you square that, that's equal to half. And probability of Alice getting 0 and Bob getting 1 is 0 because that state doesn't exist in this superposition, and nor does the state 0, 1 where Alice gets 1, Bob gets 0, because again that state doesn't exist here. So these are correlated. So whenever Alice gets 0, Bob will get 0, and whenever Alice gets 1, then Bob will also get 1. And so this can happen regardless of the say the distance between these guys. as I said, they could be opposite ends of the Earth or even opposite ends of the universe. So it's basically as if these particles somehow are kind of twins, so that they always get the same outcome. So that sounds maybe quite strange or perhaps even amazing. So you might think, wow, okay, so maybe these this quantum mechanics has some super correlations, and actually just with this result, it's actually not actually yet amazing, because you can actually do something similar with regular probabilities. So for example, say I had this gun that just randomly shot, blue balls and red balls, and say I arranged it so that the order of these, balls and these guns were, exactly the same, and then so I kept on shooting them towards Alice and Bob. And so in this case, basically, again, they just always arrive in pairs. Alice and Bob always gets the same colored balls. You never get the result of red ball, blue ball, or blue ball, red ball. Basically because I've set it up in that way, and so I can always make classically correlated probabilities. In fact, having correlations is of course nothing inherently quantum mechanical. It's just things are correlated. If it rains, I want to go to the beach. Things are always correlated. Sorry, if it rains, I want to stay at home. If it's sunny, I want to go to the beach. So things are always correlated, and that's not inherently anything quantum mechanical. But here's where it does get kind of amazing. So quantum mechanics has another trick where you can actually measure the state in different bases, right? So the key thing here is to notice that the entangled state can be written as, so we can rewrite this state in terms of this plus minus basis. So we just do the same kind of thing as we've done in previous lectures. So we can substitute the definition of the plus and minus states into here. So 0 is plus state plus minus, and plus state is plus state plus minus. And if we substitute that and simplify that, then what happens is that so the plus plus combination here, they both have the same sign, so they get a factor of 2. So actually, I think I'm missing a square root of 2 here. Okay, so that becomes plus plus, but states like plus minus, this has a plus sign in front of it, but this has a minus sign in front of it, so they cancel, and so they do not appear in the final combination. So this is a mathematical equality where you can actually write this state, this entangled state, in the plus minus basis, and actually it looks exactly the same as how it did, but just the plus minus versions, right? So that means that what we can do is we can do our kind of same experiment, except that now Alice, changes her measurement device so that she's in the plus minus setting. Bob also does that. Bob changes his device so it's in the plus minus setting, and again the particles are perfectly correlated. Okay, so when Alice gets plus, Bob gets plus. When Alice gets minus, Bob gets minus. They never get the outcomes of plus, Alice gets plus, Bob gets minus, or Alice gets minus, Bob gets plus. They never get that. Probabilities of those are 0. So the reason why this is actually kind of amazing is because now what Alice can do is that Alice can actually decide right at the last minute whether she's going to do a 0, 1 measurement or a plus minus measurement. So imagine Alice is there going with her machine, just, at the last second just goes, okay, I'm going to do plus minus measurement. Okay. Or, okay, now, just randomly she says, okay, I'm going to switch over to 0, 1 measurement. So what would happen in that case? So Alice sort of just kind of randomly choosing which measurement to do. So then Bob will actually get in the 0, 1, if Alice chooses 0, 1 basis, Bob will get 0, 1 states randomly, right? It's going to be random, but they're going to be perfectly correlated with Alice, right? So Alice and Bob, they're going to get like kind of the same values all the time. But if Alice chooses plus minus basis, then Bob actually will also get plus and minus states also randomly. And so what is happening here is that kind of Alice, by her choosing which setting to make in the device, she's actually influencing what states Bob is getting, right? So because these 0 and 1 states, these are different states to the plus minus states, right? I mean, plus state means it's a superposition of 0 and 1. Minus state means it's also a superposition, but with a minus sign. But Bob gets 0, 0 or 1. These have no superposition. So Alice is actually kind of influencing Bob's outcomes in some way, right? And moreover, this is actually happening kind of instantaneously. And the reason why I said she does this sort of at the last minute is because so Bob actually receives this state as soon as basically Alice does her measurement, right? So if they're on like the opposite sides of the Earth, or maybe even opposite sides of the universe, then because nothing can travel faster than the speed of light, there's no way for Alice to sort of communicate like which settings she actually chose. Maybe there's some like eavesdropper that's like listening in on what Alice's um, you know, choice is going to be and communicating that to Bob, right? So basically, it rules out that possibility if it, because there's no way that anybody could communicate whatever Alice is thinking, which measurement choice is, because they're so far away that even light could not, um, is not fast enough to communicate that to Bob. So this is actually why entanglement is thought to be a really kind of weird phenomenon. So this is what Einstein famously said. It appears that Alice is causing some kind of spooky action at a distance on Bob, because apparently she's influencing Bob's outcomes just by her choice of the measurement settings. So all laws of physics, basically as we know it, are kind of like there's no real sort of action at a distance. Essentially, things like forces of gravity or electromagnetism or anything like this. All these things generally, well, basically nothing travels faster than the speed of light. Right? So gravitational waves go at the speed of light. light travels at the speed of light. There's basically no phenomenon can actually travel faster than the speed of light. But this quantum mechanics does seem to have some kind of exception, that there does seem to be some kind of influence, right? So this is why Einstein thought that there's something very strange about this theory, and possibly there was even something wrong with it, right? So you know, uh, uh, so is Einstein wrong? Maybe quantum mechanics is the exception to all these physical theories where things can travel faster than the speed of light. So, um, as it turns out, um, it does look like Alice can kind of influence Bob, but um, the way that people understand it these days is that it's still actually consistent eventually with Einstein's theory that basically nothing can travel faster than the speed of light. Um, Basically, because on average, Bob never actually can tell whether which measurement setting she made. Right? So if Alice chooses 0 and 1, as I said, Bob gets 0 and 1 randomly, or more precisely, he actually gets it with probability a half. Right? And yes, it's correlated with Alice, but he's so far away that he can't really even verify that at this point. So all he can see is just these, random values of 0 and 1. And if you actually go and calculate averages of things of x, y, and z, these are the Pauli operators that we met last lecture, then you actually find that all the values of these are actually 0. Likewise, if Alice chooses the plus minus bases, again, Bob actually, shot to shot is getting plus and minus states, right? But randomly with probability 0.5. And that randomness is actually what eventually gives these average values to again be equal to 0. So somehow this kind of random property of quantum mechanics sort of saves this general idea of Einstein that nothing travels faster than the speed of light, because actually on a shot-to-shot basis, it does look like something, this kind of spooky action at a distance is happening. But on a kind of a global scale, when you take like a lot of averages, then you basically can't tell, right? So there's a kind of a loophole here, which quantum mechanics is sort of exploiting, if you like, where this kind of randomness is actually kind of saving this kind of uh, impossibility of traveling faster than the speed of light. So basically, uh, if this was not true, then actually superluminal communication would actually be possible. That means that we could actually communicate. So say we set up all these entangled pairs, we could send one to a distant star somewhere, and the closest star, Alpha Centauri, is something like 4 light years away. So the fastest that we could communicate with Alpha Centauri is 4 years, right? So you'd send your conversation would be like, you send something, 4 years later it arrives, the guy on Alpha Centauri sends another message 4 years later. So your conversation would be like, every 8 years you'd be writing like a message, right? Text message. So, you know, um, that's basically where we're at with basically Einstein's theory. Um, you know, if we were able to do superluminal communication, then this would mean that we would be able to do it instantaneously, and the light speed would not be a barrier. Unfortunately, it looks like this, because of this randomness factor, we actually cannot do superluminal communication, unfortunately. And so Einstein's theory eventually is still correct, but you know, comes this close to this close to being able to do it. Okay. So let me just sort of wrap up here by just giving you just a couple of extra points here. So firstly, for qubits, we were just talking about this particular state, but I could have equally chosen any one of these three, or even there's actually other types of states. I could have put some phase here, or even chosen some different basis here. Um, these uh, these four states are so-called these maximally entangled states. These are states which have this kind of entangled property um, uh, that is, it's the most entangled states that you can have with two qubits, right? And these states are actually named after a guy called John Bell, and he used he used these states uh, to show actually that one of the interpretations of quantum mechanics, which is that the quantum state represents a kind of a lack of knowledge of the system, uh, can be actually testably falsified. So he showed that actually that it's possible to disprove that you can interpret quantum mechanics in a particular way using these types of entangled states. And it's quite related to this kind of topic that we were talking about today. But okay, so I won't go into it. I think for this lecture, maybe in a future lecture. But he used these types of states to show that quantum mechanics has some uh, different properties to probability theory. So you really can't explain quantum mechanics using just kind of a probability kind of framework. Okay, and as for having more than two systems, so basically the story is pretty straightforward. So once you know how to make a composite system with two systems, then you can easily extend this to three or more. So essentially, you just kind of do the same thing. You just find all the different distinct combinations of states that your, say, three-party system could have. So here we've got Alice, Bob, and this time Charlie. So if each of them have this d-dimensional system, then the total number of distinct states here would be d cubed, because there's like d cubed combinations of states that you could have. Or if you had m systems, so Alice, Bob, Charlie, Dave, Yvette, so forth. Then for m systems, then the total number of combinations, and so the total dimension of the composite system will be d to the power of m. So essentially, the state here you would write as again uh, uh, some some tensor here. So that's basically just some higher dimensional matrix, basically. So you have some more and more labels here, so NA and B and C and D and so forth, and each one of those combinations has some coefficient. That's basically all that's it. And the sum has to go through all the different combinations too. And an independent state would be written as basically, again, the tensor product of this and anything that cannot be written in this form would have some kind of entanglement. In fact, this is one of these areas that is still being investigated today. So for two systems, it's actually fairly well known how you sort of find entangled states? How do you even quantify how much entanglement you have? But for more than two systems or three systems, it actually gets very complicated because there's different types of entanglement, and people try and classify different types of entanglement. People try and quantify how much there is, and so forth. And that's some of the research that I also am involved in, but that's basically ongoing as a community. Okay, so I think that is all for today. So as usual, if you have any questions, then please feel free to contact, and we'll continue with this next week. So thanks for listening, and see you later. Bye.